This is part 3 of the course about various amplifier configurations. The first circuit we will study is the common source amplifier with source resistance, where we have an amplifying MOSFET with input at gate, output at drain, and this is biased by a current source, which we can assume for now that it's ideal. We show that there is a load RL. The load RL may also include, in the small signal analysis, the output resistance of the current source. So if the current source, is not an ideal source, in the signal analysis, we will replace it by its output resistance. So this output resistance in signal analysis would be connected between drain and supply, but supply is signal ground, which means that it will be, if I have an output resistance for this, then this output resistance of the current source RO of the current source I, and the signal analysis would appear between the drain and signal ground, and therefore it will be in parallel with RL. So I can include it in RL. And the main difference between the common source that we have analyzed previously and this one is the addition of this RS. So now the source terminal of the MOSFET is no longer at signal ground. This is now, there's some signal here at the source. So basically we want to see what is the effect of this RS on the amplifier characteristics. Let's start with the small signal model at low frequency, very simplified. We will also assume that there is no small RO for the MOSFET. The circuit looks like this. This is the MOSFET with its gate, drain, and source, and there's no small RO. So this is the simple low frequency small signal model of the MOSFET. The current source, we're assuming that it's ideal for now, and therefore it disappears in the small signal model. It becomes an open circuit. The load is from the drain to ground. The input is at the gate to ground. And now the source, between the source and ground, I have RS, the resistor that we added. So the first thing we notice is that the input is no longer equal to VGS. When there's no RS, VGS is equal to VI. Now, VI and VGS are not the same. VI is the potential here from ground to gate. VGS is the potential here from ground to source. And then there is this potential across RS, which is the difference between VI and VGS. So VI is VGS plus the drop in RS. So what is the current that's flowing in RS? It's actually GM VGS, which comes here and creates this potential difference across RS. So the potential difference across RS is the current GM VGS times RS. And the input is therefore VI equal to VGS plus the drop in RS. This is the drop in RS, the current in RS times RS. And I can write this as 1 plus GM RS times VGS. What about the output? The output, this same current actually flows up in RL. And this means that the output is minus this current, GM VGS, times RL. And now we can divide to find the gain. And we get minus GM VGS RL over 1 plus GM RS times VGS. So VGS cancels and we get minus GMRL over 1 plus GMRS. And if RS is 0, to quickly verify, if RS is 0, then what do we get? I get minus GMRL, which is expected. This is now a result that we have seen on multiple occasions, and maybe we can just memorize it. The common source or common emitter gain is minus GMRL or R prime L. And if RS is 0 here, we get VO over VI, this familiar result, minus GMRL. But if there is an RS, then it enters here, it's multiplied by GM, and actually it reduces the absolute value of the gain by this factor, 1 plus GMRS. So if the gain was minus 40 and 1 plus GMRS is 5, then U gain with RS would be minus 40 over 5. So it drops to minus 8. In absolute value, it goes from 40 to 8 because of the presence of RS. So RS reduces the absolute value of the gain by this factor 1 plus GMRS. What about the input resistance? What's the input resistance in this case? The input resistance is always VI over II, and this is the input current, but there's an open circuit here. At low frequency, II is 0, and this means that the input resistance is still, whether there is an RS or not, the input resistance is infinite because the input current is 0. All right, so now we have voltage gain, input resistance. And what about output resistance? The output resistance here is let's use the definition. I would disconnect RL, replace it by a test source, V test, and I want to find I test. So this is replacing the load. This is GMVGS, RS. And when I do the output resistance calculation, I set VI to 0. So there's no VI. VI is 0. I replace the input by 0. And this is the gate, the drain, the source, RS, and GMVGS. And I want V test over I test. Well, if VI is 0 and VI is equal to VGS plus GMVGS times 1 plus VI is VGS into GMRS plus 1, right? And VI is 0. If I solve this equation, when VI is 0, I get VGS 0 because GMRS plus 1 is definitely not 0. So solving this equation here, 1 plus GMRS, which is the input, equal to 0, means that VGS is 0. And if VGS is 0, this means that this current is 0. So if this current is 0, I test is 0. So V test over I test, which is the output resistance, with VI 0, so this goes to infinity, which means that the output resistance also in this case is infinite. So the output resistance is infinite and the input resistance is infinite. We got this result because we neglected small RO. If we include small RO, then we will have a finite output resistance. So let's do that. Let's see if we have small RO, if RO is not very, very large, or we don't want to simplify the analysis by neglecting it. If RO is there, what happens? RO would appear, as always, between the drain and the source. So my previous circuit, now I modify it and include this additional resistor. small RO between drain and source. And now I need to repeat the analysis. So now instead of having a single loop, I have multiple loops, but I can do a simple transformation and go back to a single loop. So this is the transformation that I will do. I will replace this parallel combination of a current source and a resistor with a series combination of a voltage source and a resistor. And if I do that, I will get this. So now this voltage source, this one, in series with RO is replacing this current source in parallel with the same RO. And for this to work, the resistor is the same, and the voltage source would be the product of the current value GM VGS and the resistance RO. So GM VGS RO or GM RO VGS. The polarity, because this current is pointing down, the polarity of the voltage source would be plus towards ground. And with this, I'm back at having a single loop, which kind of makes the analysis simpler. And let's find the current in this loop. I have one voltage source and 3 resistors. So this is the current we're talking about in this loop. And the current, therefore, would be the voltage source divided by the sum of the 3 resistors. So GM RO VGS, the voltage source value is GM RO times VGS divided by the 3 resistances, RO plus RL plus RS. So that's the current. And now we know that the output is minus I times RL and the input is VGS plus I times RS. So the output is minus I times RL because I is flowing up in RL. So we get this expression, and the input is VGS plus the drop in RS. So VGS plus I times RS, and we get another expression for the input in terms of VGS. Both the output and the input are in terms of VGS. So now we can divide to get the gain, and we get this expression minus GMRL over 1 plus GMRS plus RL plus RS over RO. Again, it's helpful to verify that we would get the same result if RO goes to infinity. The result that we got when we neglected RO, we assumed that it's infinite, was minus GMRL over 1 plus GMRS. So let's verify if this RO here goes to infinity, then RL plus RS over RO would go to 0, and I get this. So that's verified. Also, if RS is 0, then I get minus GMRL as I expect. Another verification that we can do is, what if RS is 0, but there is an RO? And you can easily show that then you get minus GM RL parallel RO when there's no RS, which again is the result we expect. This is the R prime L that we had previously. So this is when RS is 0. So this gain expression, therefore, is a general expression when there is RS, when there is RO, and it reduces to the other simpler expressions when either RS is 0 or RO is very large. So did RO help? No, actually RO causes the gain in absolute value to drop further because RO is not infinite. I will have this RL plus RS over RO term that further reduces the absolute value of the gain. All right, what about input resistance? This is not affected by RO because the input current is still 0, whether there is an RO or not. The input current is still 0, and Ri is infinite. Output resistance, the output resistance is affected by RO. If I replace the load by a test source, I set the input to 0, RO would still be there. And I'm not sure if GM VGS would be 0 in this case even. Would it? Let's apply the definition for output resistance and see what we get. So this is the circuit with VI 0. And again, I'm applying the definition. VI is 0. RO, this is our I here with our test source connected here. We test, and I want to find I test, and then calculate the ratio V test over I test when I disconnect the load and replace it with the test source, and I set the input to 0. So this is the situation now. And I cannot really say that VGS would be 0 in this case, because there's some current coming from V-test, and so it will flow here, and something will flow here. So maybe we should do a circuit analysis. Or notice that this circuit can be redrawn. And it's not easy to do to notice that. It's not it's something that you'll have like to rotate RS and then look at the circuit from above. But if you rotate RS, if you take this and rotate it up, this is the circuit becomes like this. And if you look carefully at this configuration, this actually is the RXY calculation that we did previously. So the output resistance here with the small RO in there becomes an RXY, and you can say that RO, the output resistance, is Rx plus Ry plus GM Rx Ry, which is in this case small RO plus Rs plus GM RO Rs. Of course, this may not be clear, but if we do a complete circuit analysis, and we can do that, I mean, it's not that hard. It's 2 resistors and 2 sources, and maybe 1 or 2 equations will solve it. If we solve this using just regular circuit analysis without knowing anything about RXY, then we will get V test over I test, the exact same result, Rs plus RO plus GM Rs RO from the circuit, or use the formula RXY after redrawing the circuit and showing that it's really an RXY circuit, and therefore the resistance is the same expression that we would get if we do regular circuit analysis, RO plus Rs plus GM RO Rs. Now we will use this RXY formula to now come up with a new rule for MOSFETs. And the new rule states that if you're looking into the drain of a MOSFET with gate at DC, so no signal, and the resistance Rs between source and ground or some DC level, a small signal resistance RO plus Rs plus GM RO Rs is seen from the drain to ground. So this is, remember the rules that we talked about, looking into the drain, or looking into the collector, or looking into the base of a BJT. Now we have a new rule in this set of rules, and this is for MOSFETs, looking into the drain with no signal at the gate, but with a resistor between source and ground. So what do we see? What does this rule state? The resistance that we see is equal to small RO of the MOSFET plus Rs between the source and ground plus GM RO of the MOSFET times RS. So let's use this let's apply this first to a very simple case, which is something like this. So let's say I have a MOSFET and there's some DC voltage here. So no signal. Whenever I have a pure DC, it means no signal, signal ground. So that's the condition to apply this rule. And I want to look into the MOSFET drain. This is the drain of the MOSFET. So if I'm looking into the drain of the MOSFET, it means that there is a test source at the drain, and I want to see the resistance seen by this test source would be V test over I test again. So what would V test over I test when there is an RS? So this is exactly what the rule is saying. When you're doing something like this and you want to see the resistance looking into the drain, this V test over I test, the resistance seen is RO of the MOSFET plus RS plus GM RO RS. So that's a nice result that we will actually use often. If RO goes to infinity, the whole thing goes to infinity. If there's no small RO, then this also goes to infinity. So the test source would have no current flowing out of it. But if RO is not infinite, we will get something. We'll get RO plus RS plus GM RO RS. The other thing we notice here is that this is bigger than much bigger than RS because it multiplies RS. This is RO plus 1 plus GM RO RS. So this is bigger, much bigger than RS. The reason we say much bigger because this ratio for a MOSFET is usually large. GMRO for a MOSFET is a large number, usually in the tens or more. So this is much bigger than RS. It's also bigger than RO because we can write this as 1 plus GM RS times RO plus RS. And this is definitely bigger than 1 and sometimes much bigger than 1. So this resistance that we see looking into the drain is bigger than RO and bigger than RS, and often much bigger than RO and much bigger than RS. So it's a large resistance. So let's apply this rule in some other situations. Let's consider a situation like this. I'm looking into this node with a resistor here, R1, a resistor here, R2, and some DC level here at the gate. What is the resistance that I see now here at this node? Well, this node is definitely not the drain of the MOSFET. The drain of the MOSFET is here, so I can't directly apply the rule that I have. This R1 would be in series with what I see looking down into the drain. So this I will see first R1, and then in series with it, the resistance looking down into the drain of the MOSFET. And now looking down into the drain of the MOSFET with gate at DC and R2 between source and ground, I will see here RO plus R2 plus GM RO R2. What would I see here at this node? I will see R1 plus this quantity here because R1 is in series with it. Let's take another example. Some DC V1 here. And another DC level V2 here. And I want to find the resistance seen looking into this node here. And let's call this R3. So what is the resistance that I see looking into this node? Here, I will see the resistance looking down into this drain and parallel with the resistance looking down into the other drain. So for this one, what I have here is a MOSFET with gate at DC and an R3 between source and ground, and I'm looking into its drain. So I will see RO1 plus R3 plus GM1, RO1, R3. This is what I see here at this drain. And at this drain, I will see just small RO2. And the reason is it's a rule. And I can also consider that this is the same case as this one with zero resistance here. And if I apply this rule with zero resistance here, I will only get RO2. So I can either apply this rule with zero resistance or the previous rule that says if I'm looking into the drain with no signal here at the gate and no signal at the source, I will see a small RO of the MOSFET. So this is small RO2 here, and this is this expression. And here at this node, what do I see? I see them in parallel. So RO2 in parallel with all of this stuff here. And we can do other things like, well, here's a more complicated one. So some DC voltage here, V1 DC, V2 DC. And I want to see the resistance looking into this node here. And let's call this MOSFET 1 and this MOSFET 2. So what is the resistance that I will see for such a circuit with two MOSFETs? And they both have some DC voltage at their gates. And I'm looking into the drain of the one of M1, which is above, kind of above M2. So what do we see in this case? Now let me start here. If I'm looking down into the drain of M2, what do I see? If I'm looking down into the drain of M2, what's the situation? I'm looking into the drain of a MOSFET with no signal at the gate and no signal at the source. And there is a rule for that. If what I will see is small RO2. So in my signal analysis, what I have is equivalent to having M1 with a DC at its gate and an RO2 between source of M1 and ground. And this is my I. So what is the resistance looking down into the drain of M1 when its gate has DC and its source has RO2 to ground? Now I can apply the rule, and the rule tells me that this will be RO1 plus RO2 plus GM1 RO1 RO2. So this is what I will see in this situation. When I have two MOSFETs, I will get this kind of resistance looking into the drain of the upper one. Of course, they should have both DC at their gates. So these rules kind of simplify the analysis, and we will try to rely on them in the rest of the course and avoid doing regular small signal analysis by replacing the MOSFETs with their small signal models or the BJTs with their small signal models and doing KVL and KCL and nodal equations. We just try to avoid and use these rules. And you see that they kind of simplify our analysis a lot. In many cases, we're after some resistance value or some gain value. And there is on the Moodle page of the course, you will see that there is a list of rules, list of formulas that you can use. So there is a document that has all the resistance rules. So if you want to find the resistance looking into some terminal or some node, there is a list of rules for that. And there is also another document that has the list of rules for finding the gain of various amplifier configurations. And these are the rules that we will rely on much more than doing regular circuit analysis because they really simplify the circuit analysis a lot. The common emitter with RS is kind of similar to the common source with RS, but as you know, for the BJT, there's the RPi. So the input is at the base, the output is at the collector. The emitter now is no longer grounded. I have RS from emitter to ground and the RPi. So what do we get in this case? Again, I would like to find the gain, the input resistance and output resistance. The input resistance of common emitter when there is an RS. So need to find VI over II. V pi is R pi times II, and VI is V pi plus the current in RS times RS. The current here is the sum of this current plus this current. So II plus GM V pi. We can now rewrite as R pi II because V pi is equal to R pi II. Same here. And we get VI over II now. R pi plus RS times 1 plus GM R pi. But we know that for the BJT, GM R pi is beta. So the input resistance is therefore R pi plus beta plus 1 RS. So this is an additional component that we see now when there is an RS. If RS is 0, the input resistance is simply R pi. And we know that. There is a rule for that. If I'm looking into the base, the emitter is grounded, I will see a small signal resistance equal to R pi. If the emitter is not grounded, now I have another rule, which is R pi plus beta plus 1 RS. So this RS, I see it multiplied by beta plus 1 and added to R pi. So I don't see simply R pi plus RS. It's R pi plus beta plus 1 times RS, and beta plus 1 is a large number. Beta plus 1 can be 50, 100, 200. So this is a new rule then that we will come up with. The resistance seen looking into the base of a BJT is R pi plus beta plus 1 times the resistance between the emitter and signal ground. So this resistance between the emitter and signal ground appears to be beta plus 1 times larger when looking into the base. This is called the base reflection rule. Notice on this slide, the fine print, that the above rule applies when RO is very large. If RO is not very large, because we derived this rule without RO, if RO is not very large, then this rule would not give me an accurate answer. The error would be still acceptable, but it will not be the exact answer that I will get if I do a full circuit analysis. So always make sure that you know the conditions for your rule and when it applies and when it doesn't. The rules that we had previously derived, they apply when we have certain signal grounds at certain nodes. I think this is the first one where the rule applies if RO is very, very large, and it doesn't if it's not. But still, it's a useful rule, and it simplifies our kind of intuitive analysis of especially input resistances for these BJT amplifiers. What about voltage gain for this common emitter with RS? We will just use the MOSFET result because the analysis is very, very simple, and the result would be actually very similar. In the case of the MOSFET, I got minus GMRL over 1 plus GMRS. In the case of the BJT, it's minus GMRL over 1 plus GMRS over alpha. What is this alpha? Alpha is beta over beta plus 1. And it's a very, very close to 1. It's a number that's very close to 1. Because beta is very large. So alpha is like 0.98, 0.99, 0.995. And therefore the voltage gain is almost minus GMRL over 1 plus GMRS. And that's the same result that we got for the MOSFET. Again, we're assuming that RO is very large. So no RO again here. If there's an RO, I get like a kind of complicated expression for the gain. What about output resistance? Again, I will try to recycle now previous results. So whenever I see something like this, what I will try to do is to avoid doing full circuit analysis and try to see, is there a result that I know? Is there a rule that I've seen that can give me this answer without doing full circuit analysis? And if you look carefully at the circuit, we want our eye is here, and we want to find the resistance seen looking into this. Well, this R pi is, because I'm doing output resistance and I set VI to 0. When VI is 0, this R pi, the base, is grounded, and this R pi is actually between the emitter and ground. So R pi, when I'm doing output resistance calculation and setting VI to 0, R pi becomes in parallel with RS. Even though it's between emitter and base. But if I'm doing output resistance calculation and set VI to 0, R pi now appears in parallel with RS. And now the circuit becomes very similar to the case when I'm looking into the MOSFET drain with a certain resistance between the source of the MOSFET and ground. So we would recycle the MOSFET result and say that RPi and RS are now connected in parallel, and they appear to be like what we call just RS in the MOSFET case, when we were calculating the output resistance of common source with RS between source and ground. So I will use that result and use the MOSFET formula, but instead of just RS, I will modify it and say now it's RPi parallel RS, because in the case of the BJT, I have this RPi, and it appears in the output resistance calculation in parallel RS. So I will use the formula and just modify it. I don't need to repeat the calculation again.